Hello! It's time to prove Fermat's theorem. And this proof can be found in page 279 of your textbook. It can also be found in your class notes if you take notes, because we actually proved it together in class. It's a nice proof, and I think it's not too difficult to learn and understand and replicate. So let's do it together with the video as well. Feel free to skip, pause, whatever works for you. We're going to start with the statement. The statement is, for Fermat's theorem, if f, a function, has a local max or min, doesn't really matter which one, at a point c, x equals c, and f prime at c exists, then you can conclude that f prime at c is 0. This is kind of the converse logic that we use for when you're trying to find all your critical points and find local maxes and mins or absolute maxes and mins. So this is saying if you had a guaranteed max or min, then you know the derivative is 0, but it has to exist. Why don't you think about a case where you had a local max or a min, but this derivative didn't exist, and then you knew you couldn't conclude that. That's a neat thing to think about. All right, let's prove. So for the proof, PF for proof, so we're going to suppose that f has a local max, because it doesn't matter whether it's a max or a min. The proof's going to go exactly the same, so you're not really losing any generality, so to speak. So we're going to suppose f has a local max, and we're going to say that that happens at x equals c. Then, the first thing we're going to notice when we use this to develop a proof is that the value f at c is greater than or equal to other nearby values. So I have to say near c. Okay. And a really good idea might be if I can just make a picture. Okay, so we had a local max, so say it looked like that. And then that's the max. And then around in this little area, we can see that these f of x's are smaller in value than the f at c. So this could be x equals c. So maybe keeping this in mind could help you with the proof. So anyways, since this is true, we're going to do something, and we're going to call it a star, because we're going to refer to it later. You might remember this from class. So we're going to let x equals c plus h for a h greater than 0, important, but small enough for what? Small enough for this to hold. So small enough for f at c to be greater than or equal to f at c plus h. So then what we have in the little picture is that this would be c plus h. Well, this would be the value at c plus h, actually. C plus h would be kind of over here, a bit to the right of c, because h is greater than 0. So we're going to use this fact. And if you look at it, it's got a c and a c plus h, and it kind of is supposed to remind you at this point of the first principles definition for a derivative. That's where you're supposed to go next, to try and create the first principles definition of a derivative, except there's not an equal sign. You have a less than or equals, no big deal. So I'll show you how to do that, but we're going to keep the picture up. So just give me a second here. So remember that statement I just erased at the bottom. We're going to use that. Okay. So if I hadn't run out of space, I would have just continued, and I would have said that that implies that f at c plus h minus f at c is less than or equal to 0. Yeah, I had to move things around, and then I had to multiply through by a negative sign in order to get this line. And the reason why you know you want this line is because you want it to mimic, again, that first principle of f of x plus h minus f of x over h. And now we're going to divide by h, obviously, to continue to mimic that. So therefore, f at c plus h minus f at c all over h is still less than or equal to 0 over h. Nothing happens to this inequality for h was positive, right? So that's equal to 0 over here. So you know that this almost derivative looking like quotient is less than or equal to 0, right? It might even be helpful if we just, this is really the information that we need. Now, what we're going to do is we're going to take limits on either side of this expression. And you know you can take limits on either side when there's an equal sign, but we are giving it to you for free, this term only, that you can take the limit across this inequality as well for free. And this is what you have to do. You have to take the limit as h approaches 0, but from the right, because h is positive. It doesn't make sense for h to approach 0 from the left. So just take it from the right of this whole thing, and then you can analyze. And that's less than or equal to the limit as h approaches 0 from the right of 0. But you know that the limit of 0 is just 0, because the limit of a constant is a constant. So if you skip that one little step, no big deal. This is what you get by taking the limit across both sides of this. Okay. Now, Fermat's theorem gives us one more piece of information. Not only is there a max, but we know that the derivative exists there. So I'm going to use that. So since f prime at c exists, f prime at c is indeed equal to this. Now, why is that? Well, if there had been no plus sign here, you would have agreed that the first principle definition of f prime at c looks exactly like this. But if a derivative exists, it's equal to its right-hand derivative, and it is equal to its left-hand derivative. So this being the right-hand derivative, it's a different way of writing the derivative if you do know that it exists. So f prime at c is equal to the limit as h approaches 0 from the right of f at c plus h minus f at c over h. I get that it is equal to the limit as h approaches 0 regardless, but just we need to use this fact, right? So this is less than or equal to 0, which when you link these together gives you that f prime at c is less than or equal to 0. So I'll say therefore f prime at c is less than or equal to 0. And then I'm going to erase the board again. So make sure that you have this so it makes sense. And then we're gonna see if we can show that not only is f prime at c less than or equal to 0, but by a very similar argument is greater than or equal to 0. And then we'll be able to conclude Fermat's theorem's conclusion. Okay, the second part, showing the greater than or equal to part for this, is not that difficult because we kind of laid down the framework. We'll just start at the point we label star. So, now, at part star, we are going to let x equals c plus h the same way we did before at star, but this time we're going to do it so that we have a value over to the left of the max. That is, we need h to be negative and small. Okay, so let x equal c plus h for h less than 0 such that we still have that this f at c value here is greater than or equal to f at c plus h. That's still true, because whether h is small and positive or small and negative, the max is still cushioned in the middle there, so it's the higher one. So I think it's time for us to create the same thing we did before, just keeping in mind that h is 0. H is 0. Can't believe I said that. That h is negative. Got it? Okay. So therefore, or that gives that f at c plus h minus f at c divided by h. You would do exactly the same thing, but when you divide by h, your inequality would switch. And instead of being less than or equal to 0, it would be greater than or equal to 0, which is 0 over h. So then we would get that the limit as h approaches 0 from the left of f at c plus h minus f at c all over h is greater than or equal to the limit as h approaches 0 from the left, because h is negative, of 0, and that's 0. And by the exact same logic as before, this is actually the left-hand derivative for f at c. So therefore, f prime at c is greater than or equal to 0. And you don't need to really do much explanation. It's such similar logic to what you just did the first time you used a positive h. You don't need to do much else. You can just conclude and say, therefore, f prime at c is greater than or equal to 0, and it was less than or equal to 0 in a line above, so it must be that f prime at c is equal to 0. And that concludes Fermat's theorem proof.